Here again with part 2 of chapter 5, equivalent expressions. The big ideas this time, we want you to be able to identify expressions that are equivalent. We want you to use these things we call polynomials, these interesting little symbols. We need you to tell which ones are which ones belong together, which ones don't. It's called gathering like terms, and it's very important as we lead you into a better understanding of algebraic sort of thinking. Now, if you're not familiar with algebra, algebra is a system that uses unknowns. If you've ever said 3 times the number is 12, you've used algebra, because you could, instead of 3 times a number, you could have just as easily said 3 times a number is 12. Now that system of using unknowns to help you solve a problem, that is algebra. That's classic algebra. We're doing lots of that in no time. Don't you worry. So what we need to do first is we have to identify different critters. I always love to use my zoo analogy because we've got things that we have to identify. We have to know what these things are that are called terms. So terms, variables, exponents, coefficients. We'll make it make sense. Don't you worry. A coefficient is what I like to call a counting number. It's how many you have. At times, it's hard to tell what the coefficient is because even if you went to a zoo, and let's say we look at a cage of lions, and we'll let L represent lions. If you let L represent lions, if there's at least one there, the understood coefficient is 1. But if there were more than one lion, okay, and that's one kind of thing, one kind of term, if you will. Let's say there were 3 lions, the coefficient would be 3. So it says how many of a particular term you have, and we'll outline all the different terms coming up here shortly. Looking below at A through F, I see negative t, 4d squared, and these are things, and they're all quite different. The exponent unit was pretty useful for this because in the exponent unit you learned about the fact that an exponent had a base and it had a power. So a number which has a base and a power, we say, well, that's a value with an exponent. Let's look at this one first. Zoom in a little bit. There we go. The first thing I do is I highlight how many we have. The coefficient is the number that comes before the letter. So in this case, you say we have 4d squareds. So we'll identify the coefficient as being 4, and the variable, or the thing, is a d squared. Now you need to write not only a letter, but its power, and that makes it unique. That's its identity. If we look at this minus t here, well, we know that the variable, or the unknown, is t. Now how many do we have? I'll zoom in a little bit. It's the negative of t. Well, if I write in a minus 1, like that, oh, now I get it. It's minus 1 times t. The number out in front is a negative 1. Oops. Undo. There we go. So our coefficient needs to be written in there as a negative 1. Now when we look at the number of variables something like this has, we say, well, that doesn't have any variables at all. It's the number 12. There's nothing varying about that at all. We're certain of it. We call the number 12 a constant. So it doesn't have any variables. So we say none. And this is my special none symbol. Okay? Definitely none. Constant values don't have variables. We know exactly what they are. And constants are just how typical counting numbers. -1, -2, 3, 4, 8, 10 million. We're certain of it. There is, when you go to say a coefficient of something like a 12, well, there's a 12 sitting there. There's one 12 sitting out in the open. So I don't really like to say that 12 has a coefficient. I don't really think it's applicable. You might have noticed the trick is to look at the number which you would write in before the letter. If I do this, it becomes pretty apparently obvious. Our coefficients are -8. There's one of these, and there's -1 of these. I like to think of it in terms of animals. This animal down here, if you see the letters together, if they're being multiplied together, or if they're being divided, well, they're together. So I say, well, this is like a DE animal. You can think of it as there being -8 DE animals. And when I use this analogy in school, kids are like, well, what do you mean -8? I said, well, what if DE was a kind of bird and 8 died? You take away 8 of them. They'd be like, oh, no, okay, I get that, right? And that's the zoo conditions are like that. You can add animals, you can separate them into pens, you can let them range, move around in the zoo, but at some point you're going to have to bring them together, and some of them do in fact die. So the coefficient is like counting how many animals you have. Good way to think about it. It works really quite well. The variables in this case, think of the DE as one thing. Because it is DE, D multiplied by E, this is the letter B. We'll say those are, there's one bunny. And C squared, well, I told my students today, if C represented cat, then maybe mountain lion represents a cat squared. Just a lot more to it. You have to not only include the variable, but you have to understand it's one variable. I like to write in the exponent here. I want you to understand that it's C to the power of 2. The variable is C, I get it, but it's a C squared. And this will come up a little later when we start playing around with algebra tiles. You get another example here. Find the constant. Okay, let's get out the highlighter. I'm looking for something that's just a number. There we go. 17, and I'll write the number. I get that it's B. 17 is the constant. A binomial with 2 variables. Okay, so I go hunting below. Let's find something that is a binomial with 2 variables. Okay. This down here has 2 very different variables. So we'll say 5x minus 3y. Okay, that works. Something where you have a -1 coefficient. Well, I see a minus hanging out in front of that. A -m. So we can cross that out. Done, done, done. -4 is the coefficient. -4 x's. Got that one. A binomial with a degree of 2. So we have to, now we look at the last 2 that we have and we say it's got to be a binomial. That means that there are 2 different terms. Well, as soon as I see it, I clue in on this one. Because we've got a y squared and a y. Well, that's a y squared and is like this. And when we use algebra tiles, we say, okay, if it was a square, we would use a tile that looks like a square and say that's what a y squared tile looks like. Whereas a y tile, we just sort of leave sort of thin like that. And in this case, we say there are 2 of them. And I'll use negatives just to help you get the idea that there are -2 of them. So 3y squared minus 2y. There we go. Now it does have a degree of 2 because our little champ here, remember when you look at the degree of a polynomial, you sort of look for who's the captain. You look at the variables and you check out their exponents and you do this little game of adding them together. You look at this guy and you look at this guy. Now it's a separate comparison. The captain is that definitely that y squared term. It's got a greater degree, right? A y squared is bigger than a y to the first power. So this is a second degree because of that right there. By a process of elimination, the very last thing we have is a 2ab as our monomial, because a monomial is sitting all alone. It's not being added or subtracted to anything. This monomial here, and I'll erase this when I'm done, if you said 2ab plus the constant value of 1, that would make that a binomial. But if I hit undo, it's all alone, not being combined with anything. So it's definitely a mono or solo term. Like terms, by definition, for two terms to be alike, they have to have, well, let's give you a solid example. Let's say you have 3y squared versus 2y. Now, these are not like terms, and I chose this to make a point. This is like 3 times y times y, and this is 2 times y. This is a totally different beast. When you lay it all out on the table, you can see that it's very different. This is 2y. When we get to the algebra tiles, although I'll jump into it a little bit here, this is like saying we have 3 of these squares, these y squared terms, and here we have 2 of the y rectangles. We like to call these y squareds. Well, squares are really useful because to help identify them, we draw them as squares. And you can see that those are not the same thing. You can't combine these. You cannot put them together. Because if you asked yourself a question, well, what the heck would it be? A 5 triple y or something like that? No. You've got 3 of those squares over there and 2 of those smaller things. In this case, we're using rectangles. So like terms, and I've got just enough room here, they have to have the same variables, and they have to have not only the same variables, but they have to have the same exponent. Again, going back, 3y squared has an exponent of 2, whereas 2y has an exponent of 1. So these are not, and that's a not equal sign. These can't be combined for that reason. Okay, so along comes the heavy lifting. Circle like terms in each group. For the purpose of brevity, I'll go over a couple of these because there's a lot here. And I want to switch colors because although purple is my favorite color, it's slowly driving me mad. Here we go. When I go to collect the like terms, I look for similar animals, similar beasts. And I'll start with this x, and I'll say, is there another x squared out there? Doesn't look like it. This is an x to the first term. Even though you might look at it and say, hey, that's an x, they're both x's, remember that 1 is, if you think about it, is an x squared, where our negative x is represented by this shape. They're not the same thing. So I'll just click undo a little bit. So we'll say we have an x squared all alone. Nobody else to put in the cage with it. There's one of those. What else have we got? We've got a y squared, right? No others of those. We've got some, let's go to the single terms here. What do we got there? There's a 4x there, and this guy is also an x. Now the understood power is to 1. As soon as you see that, you say, hey, wait a minute. There's 4 x's there and a negative x. Well, what if you said like 1 died? You had 4 here and you take away 1 x here. That's interesting because we can group those. So if we're going to circle them, which is originally what it said. There we go. I didn't want to use purple. Go to green. These guys are the same, and you can combine them. Let's sort of speed this up. You have a 7a here, a 1.5a here, and one more over there. Similar terms. You can add all of their coefficients together. Gets a little bit more peculiar as you go down. In E, the first thing I'll look at is the ST is like a beast. Let's use the ST and beast. Where are any other ST terms? Well, there's one there. It's like a 0.75 or 3/4. Here's a -1 ST. And when I look out into the rest of the examples, there's no other STs. I see an S, a T, a P squared. Very different. Here's a JK that would go with this JK. Here's one that apparently died. There we go. What I'm looking for, the reason why I identified the JK is it's J multiplied by K. It's one term. We don't know what it is until somebody comes around and says what J and K are. But we do know the pattern is multiplying J times K. It's like one kind of thing. Okay, so the JKs are sort of a unique thing. They're like a mathematical beast. So we'll group them all together. We'll get them all together and figure out how many we're talking about. And that'll help us down the road. Perhaps we'll use them in a formula. I guess by JK we could have called them jerks, right? There's half a jerk there, one jerk died, and 6 jerks showed up on the scene. Hey, if that floats your boat, I say use it. When we go to combine like terms, we're essentially adding the coefficients. We're counting them up. You're like a zookeeper. In the last example, I was talking about jerks because it's fun. Really, how many jerks are we talking about? Well, we could just have easily talked about lions like we did at the start of this lesson. How many lions we got? Some died, some get added, a couple more come from that other zoo. We're adding the coefficients, which is in front of our term. So example, we use the one from above. Let's say we had 6 JKs minus 1 JK, and you add in half a JK. Okay, well that's probably good for 5.5. So we're going after these right there. We say that's 5.5 JKs. Now you got to be careful here. You can't take dissimilar things and put them together. If I was at a zoo and they said, hey, put those zebras in a pen. Well, I'm going to put the zebras in a pen, but I'm not going to put them in with the donkeys. I'm not going to put the Z's with the D's. They're not like terms. They're different variables, right? And as soon as the variables are different, you can't combine them. You can't do it. You can't put the C's with the C squareds. Let me go back. If the C represented cat and C squared, well, that's like a totally different beast. I wouldn't put them together. It's going to be a bad result for the cat. And I like to use my mountain lion analogy. All right, switching from Irish green here, let's go to, I don't know, sort of this dusty blue. First thing I go after are sort of the larger size terms. You've got 3m squareds here, and 1 died there. There's like a -1. 2m squareds. Okay. Now this 3m is kind of hanging out here on his lonesome. He's positive, so you notice I'm combining it, right? It's being, these are kind of in the same zoo, so I have 2m squareds there, and in the zoo, you could say I have 3m's. Now I'm not putting them together. It's not like 5m to the third. Don't do that. We just say we have this in this pen, added to the zoo, we have 3 of those m's over there, And unfortunately, we've got like 6 maybe dead crows or something, whatever you want the constant to be. Bada bing. Now I'll use a highlighter. What do we got here? Our k-squared term is there. So you notice I go after the big one first. It's a good plan. So it's like there was a death at my zoo. You could say overall you lost 8 k-squareds. Okay, I can write that down. A loss of negative 8 of those k-squareds. And then what's left? These are k to the firsts. What do we got? Ooh, oh, there's just one left. We had 5, 4 died. So that leaves us with 1k. And our last number standing here is 8. I'm very careful with my pluses or minuses there. If these values turned out to be negative, if k was negative, I would have written a negative in there. Negative and minus, you got to get used to the idea. Same thing. In other words, go left. Here we go. This is a positive value, positive 8. If I'm going to combine these, I need to have that plus out in front. Okay, rich with examples. Again, I'll hurry and go through a few of these. There we go. If we look at those two, there's a negative c squared and a c squared. Okay, so that's like negative 1 plus 1. If you had 1 and 1 died, let's say c squared represents a really large cat like a mountain lion, then you could come along and say, well, time for red, they canceled each other. They're gone. And what's left is, oops, let's hit undo. What we're left with is just regular cats, I guess. 1 died, and there's 3 there. Okay, so that's like 2 cats left. Again, I'm just taking 3c minus 1c, like that. Example below, speed up now. That is 1b squared. There's only 1 remaining. So we'll just write b squared. The coefficient of 1 is understood. And then let's look at the b to the first terms. That's a loss of 15. And then we pick up 1. So net loss is 14. 14 b's lost. See why I wrote the negative in there? It's a negative 14 coefficient. So I have to put the minus somewhere. It's got to go in front. So there's your formula. And our last one here, minus 5a, minus 6a, minus 8a. So I'm just adding with the coefficients. And then I look at what's remaining, which is 8, but it's minus 8, decreased by 8. Okay. Quite a bit to take in there. If you get a chance, get the notes blank and you can write this down. Then I guess endlessly to torture yourself, you could watch this again and again and again. No, I'm just kidding. It's great fun. Let's apply combining like terms, and let's do it with something like perimeter. It comes up, you'll see these perimeter questions all day long. A rectangle's length is 7 greater than its width. So all they've told you is the width. Okay, so my first advice, goodness sake, if W is width, write it in. And the length is 7 greater than the width. Okay, so this is like the width plus 7. I can do that. There we go. So we've labeled all the sides, and the opposites are identical. Write an expression to figure out perimeter. Well, perimeter, if you think about it, perimeter is when you take a trip around the whole outside, right? You add up the distance. So if you started on W, then you went to the W plus 7 side, came around again, you're over here now, the W side, and you finish at the W plus 7 side. How many W's is that anyways? 1, 2, 3, 4. Since they're W's, you wouldn't leave it like this. And this is what we mean by collecting like terms. There are 4 W's, and then there is the number 14. What I'm collecting here are the constants. We know there's 7 there and there's 7 there. Constants don't have coefficients. We just add the constants. You've been doing this your whole life. There we go. Just adding numbers. Now that becomes a formula. If somebody came along and said, hey, you know, the width of that thing was 1, you'd be like, oh, geez, now I know what the perimeter was. 4 times, change our color here to red. So let's say it was, what you're telling me is if width is 1, this is like 4 times 1 plus 14. Okay, so the perimeter itself would be 18. What set of notes would be complete in math without giving you sort of a thinking example? An example where you have to apply this combining of like terms and writing of expressions. Well, in example number 6, they're going to ask you to write an expression. And it's one of those classic sort of in-school ones we all know and love, but we didn't really pay attention how much it would cost to publish something like a yearbook. Now look, a yearbook is $440. Okay, so that's the first bit of information. And each book is being sold at $8 a pop. So you can see that at $8 a pop, you're going to have to sell quite a few yearbooks just to pay for the production, the $440. So how do you express this? Like, how do you write this? Well, it's not that bad. In terms of profit, you take the number that you sell, $8 times however many you sell, and you have to take away that cost. If you go into business, you're going to learn this. You have to pay for your supplies and for your wages, and everything after that is profit. Can be written with this expression. Now, the question below says, how many books are needed for them to break even? Well, 8 times what would give me 440? That's kind of an interesting question. Interesting way of presenting it. And that's literally what some of the students do. They're like, you got to just make $440. So if we just took it $8 per book, how many books would we have to sell to equal $440? Now, you're like, Mr. Bleeker, you're doing an equation. Well, that's okay. This is just a step 1 equation. Divide this by 8 if you remember your algebra skills, because we want to just figure out how many we would have to sell, just n. And if you don't remember, there's no problem in saying, well, how many times does 8 go into 440? Long division is a survival skill. Don't reach for the calculator if you can do it this quick. There we go. 55 books. So we have to sell 55 books just to make the $440. Your profit is at $8 a book. You're going to have to realize, and I'll just draw this up here for a second. Imagine if you only sold 10 books. You're not profiting. You're in the hole. Let's change the color for a second, because red is a great color for bleeding money. Let's say you had $8 a book, and the kids didn't show up, and you only sold 10. But you still have to take away your book production cost. You have to pay that no matter what. Holy smokes, are you in trouble? 80 less 440. Yikes. You are in the hole. Now, a quick way to do this, 440 minus 80. Go like that. Let's move this out of the way. There we go. Just doing a little manual work here. 360, so where you can see the numbers come from. Now this would be negative 360. And what that means is that you're at a loss for $360. Now that sometimes happens in schools, and sometimes schools have to get out, they have to sell more books, right? They have to fundraise, because otherwise the school would be left on the hook for the contract. That's not good. So a loss of $360 would apply in this situation. So you're sort of getting the idea of how we might actually use expressions almost as if they're formulas and they lead us into equations. Okay, that takes us right to the end of our, there we go, of 5.2, equivalent expressions. This was all about collecting like terms. It's very important to be able to collect like terms, and that's it right there. Because when we get into formula work, you're going to need to combine variables, and that's really where this is headed. Not only for algebra, but for geometry and beyond. Okay, have a good one, folks. 5.2 equivalent expressions, and you have yourself a good evening.